90 minutes. Question structure, multiple choice, false, matching. For the multiple choice of calculation, so you bring calculator. That means I give you output and you become the answer. For the lab, or that search from a database, get the information from the database, and then you pick up the gene name, organism and organism name you remember, scientific name and common name, the gene length, and so you mRNA, you calculate the mRNA length, something like that. The second part, precision mapping and primer design. Primer design, you have 3 options, and then you have to understand how to set up. If you see the setup, you know the position, or you calculate the fragment, the length, the target sequence length. That's the last. Now, detail for the other lecture. The lecture after Mr. Visan only lecture 7. For the DNA markup, we have 3 genome viral, nuclear, mitochondrial, and chloroplast DNA. And you remember, chloroplast DNA present in plant only. Okay? Chloroplast present in plant only. Karyotype. This slide shows you what karyotype provides with information. Karyotype provides. Twenty-three show you allozyme and isozyme. So what is allozyme? Allozyme that the different form of proteins look encoded by the same locus. That the allozyme. For isozyme, different proteins encoded by different loci. Okay, allozyme and isozyme here. Check the definition of allozyme and isozyme. This one gives you definition of polymorphism. Polymorphism, 2 or more alternative forms of DNA sequence. Okay? Because you have, and also identify as polymorphism, alternative form of DNA sequence. DNA sequence not necessarily gene. Okay, DNA sequence. And so the difference, that's why we use a marker. For the B-cell, we need primers. So what is primer? Because you have the other term, the other drug similar to primer. But primers are new to what? Here, primer and new to templates to amplify the DNA. For the drug, what is the drug? Drug hybridize with the target sequence. Okay, so primer is from with drug. Primer is for B-cell reaction. Drug for hybridization technique. In studying rosette life, Heterosexualized, here definition, and then GT or CDG. We call motive. Motive provide what information? Provide the sequence, provide the number of neurotypes in the repeat, sequence in the repeat, that's the motive. And then here show you how to identify alleles in heterosexualized. To look at this example, I already explained how many alleles present in this gel. How many? How many alleles? 3, that's right. You just count the band, how many bands? Different. 3 bands, so that's why 3 alleles. Just look at how many bands present in this image. And then you have definition of SNP, single base variation. For the SNP, one term we call haplotype. A set of SNP on the same chromosome. The keyword same chromosome. Remember that. So I'm on for lecture 7. Genomics and proteomics. Genomics classified into structural, functional, and comparative genomics. If you study gene expressions, which one you study? Which one you study? Transcriptome and proteome. Okay, gene expression. Transcriptome and proteome. Transcriptome and proteome. But the transcriptome and proteome will vary with internal environmental condition and also depend on the tissue. Okay, transcriptome and proteome varies with external environmental condition and also depend on the tissue you isolate. Genetic map or linkage map compare with physical map. Physical map. How to measure physical map? Be spelled. Linkage map. Measure centimorgan or map unit. And then to construct genetic map, we need backdrops. Here show you the definition of backdrops and also genotype of the backdrops. The genotype of the backdrops. Individual with a non-genotype cross with one homozygous recessive genotype. That's the backdrops. And cheers. So this one show you characteristic of NGX 34 and 35 compared with the Sanger technology. This one explains about some term in web informatics, actually annotation, and actually another term not shown here. Read. Okay, read. That the short DNA sequence after sequencing show the sequence of short DNA fragment. That is read. So you de novo assemblies. De novo assembly that means merge the subgroup together into the content without reference genome. The de novo without reference genome. Here, EFT explain about EFTs. And then microarrays. This slide 51, microarrays. And now we move to lecture 9. So this one gives you the definition of domestication. And domestication undergo inadvertent genetic selection. This one gives you the definition of artificial selection. Okay, artificial selection. That intentional genetic selection. This one shows you disease traits and why we classify disease traits into quantitative traits, not qualitative traits. This slide explains about genotype. Genotype equal phenotype equal genotype interactive environment. Okay, so this slide gives you 3 terms: phenotype, genotype, and environment. Phenotype equal genotype interactive environment. This one shows you the definition of QTL. QTL quantitative trait locus. The locus contribute to quantitative variation in the traits. That's the definition of QTL. We also have the QTL. Explain the QTL here. QTL strand of DNA closely linked to the gene, unlike the trait in question. So QTL not necessarily specific gene. Okay, so this one explain more detail about QTL. And then you have the term similar QTL mapping. QTL mapping the process of constructing linked map and conducting QTL analysis, identify where the location contribute to the trait of interest. We call QTL mapping. QTL mapping, that's the process. This table shows you entity effect and dominant effect. I already explained how to calculate the additive effect in dominant effect. I already showed you how to calculate the additive based on the table, and I explained how to calculate additive effects and dominant effect. This slide explains the line, isogenic line or conchenic line. The definition of isogenic lines and conchenic lines. Marker existed selections. So that means we select a individual to be the balance based on marker, not based on phenotype. That means indirect selection. Because we select based on the marker, we don't select based on the phenotype. The marker assisted selection. Okay, and then last text. Evolution. This slide gives definition of evolution. Genetic change taking place in a group of organisms over time. So the people here, group of organisms, not individuals. Genetic variations. Genetic variation is essential for evolutionary changing, and it continues the origins of genetic variation from mutation. Also show you the other one, not create the new variation. Genetic recombination. And also crossing over, not related with one, not related with one. Only mutation, related new variation. Related new variation. And then you have definition of gene pool. Gene pool. All gene found in one population, again population, not individuals. And then you have the term gene flows, the physical movement of animals. When the individual move in or move away from population, that is gene flow. And then we construct the phylogenetic trees. We base on common ancestor, and common ancestor determined by derived traits. Derived traits character present in a group, but not in that ancestor. That derived traits. And then we have phylogenetic traits. Phylogenetic traits. And this slide explains how to construct phylogenetic traits based on homologous sequence. And also step in constructing phylogenetic traits. And then the table here show you what show you mutation rate. And mutation rate calculate per billion year, 10 power 9 years. Okay, and this one show you how to calculate the total times need for evolution, both species, human and kangaroo. If identify the time when it happened, you need to divide 2. Okay, divide 2. For example, for the humans, the mutation rate 0.74. Human with mouse, that mammalian group, the mutation rate 0.74. The phylogenetic show you here 80 million years ago. And then the total times for human and mammals, essential for evolution. If the evolution happened at 80 million years ago, what is the total time? 100. 100. How to calculate it? 100. 160. Why 62? 80 million years multiply 2. Because that you back to this calculation. The calculation will ask you the total times or when it happened. Okay, when it happened, you get the total time divided 2. But it 3 show you when. So you when. That means total time you need to multiply 2. That right? So just 2 things. Divide 2. When ask you when. Total time, it show you when here, when million years ago. That when you multiply 2. But the other way I can ask you. So we have 2 species, A and B. The protein, we investigate 100 amino acids, and we compare 2 protein, we see 12 different amino acids. And then the evolution happened 5 million years ago. Now the question asks you, calculate the mutation rate per billion year. How do you do that? How do you do it? The first one you have to calculate what? You have to calculate the average number of amino acid difference. Okay, and how to do it? Get the number of amino acid difference, divide for 100, divide for the protein sequence. 12 divide 100 equals 0.12. Okay, that's what 12. That's the average number of amino acid difference. And then you link with the time. And the time here, 5 million years ago. So continue to do, and I check your answer, and I will know you will understand or not. Okay, continue to do how to have this mutation rate per million years. Give me the number. Who can calculate? What the number? What the number? Because you have average number of difference amino acids, you link with the time, and the time 5 million years ago. And when you have the mutation rate for this time, you convert into million years. So what's the number? What's the number? Oh, give me the number. What's the number? 24. Who have different answers? Who have different answer? Only one answer, 24. Who had different answer? Quickly, we don't have time. 24, wrong. 12, that's right. Why 12? That's right, here, with you 5 years ago. Okay, so we need to calculate the time for both species. You have to multiply 2. Get the 3 thing here. Because this one ago, not the total time. You have to be on the total time. Okay, and then you set up 0.12 need 10 million years. Okay, and then 1 billion years. Now, very simple calculation. Go on for final result.